if I were a malware author today, for example, like I think I would definitely choose Rust, go with Rust, just because of like the sheer advantages that you gain in the fact that it's like much more difficult to reverse on the side of the defenders.
Navigating that added layer of complexity is exactly what we are discussing today. Welcome to Behind the Binary. I'm Josh Stroshine, and today I'm joined by Jae Young Kim, a senior malware analyst on the Flare team at Google. Today we're talking about how the shift towards modern compiled languages, like Go and Rust, is fundamentally redefining the reverse engineering landscape. We dive into the challenges of reversing complex runtimes, how obfuscation frameworks are evolving, and what the rise of LLMs means for the future of binary analysis. Let's get right into the episode. All right, joining me today is Jay. We're going to talk about reverse engineering, modern languages, and the transition maybe from learning assembly and C and some of the challenges with that to more of a modern stack. I say that maybe a little, I'm not sure how modern it is because some of these languages have been around now for quite some time. So, Jay, you've been reversing for quite some time. It seems like we typically start. I know when I started, it was learn a little bit of C, learn a little bit of assembly, and then the learning curve seemed to steepen as you got into C++ and some of the object-oriented nature. And how was it for you? Where did you start learning? Where do you think the challenges then as you got into C++ really started, and what makes that challenging, at least initially, to learn how to reverse engineer it?
Yeah, so when I started, which isn't even that long ago in the grand scheme of things, I think it was still fairly common to see malware that was more of a vanilla flavor of C, which is how I typically refer to these things. Is like it's C. There's no obfuscation. It's straightforward Win32 APIs, and in a lot of ways, those are quite pleasant to reverse in some ways because you could easily get a pretty full understanding of the program. There's no massive runtimes that you have to deal with. There's no overly complex language features. There's no crazy optimizations, like all these things, right, that make it difficult for us. So, yeah, I think even when I just started, it was fairly frequent that you would encounter samples like that when you're reversing malware. But I think in the recent years, it has quickly become that like that is not something you can expect to see so frequently anymore. So that's in some ways unfortunate because obviously that makes the job harder for us. But uh, in some ways, it's oftentimes less satisfying because you just can't spend all of the time fully reverse engineering even like a moderately sized C++ program, say. That's a significantly more daunting prospect of like fully understanding every piece than say like a vanilla C program. um, so the landscape of the type of malware that we see and like what languages and runtimes that we deal with has definitely shifted dramatically. And yeah, it's only gotten harder. It's never easier. So I think that does also maybe push the barrier to entry for people who do want to reverse malware significantly harder in today's age than when I started, which is less than a decade ago. So
I guess there's a couple of things that C++, at least when I look back, it seems like that was the language that kind of introduced these reverse engineering. I don't know if I say hurdles or obstacles, but you had things like virtual function tables to support inheritance and that polymorphic behavior, and then you had the standard template library, and maybe the standard template library is sort of a precursor to what we see today, and that you started to have to deal with a lot more boilerplate code and you know I guess bloat in the binary. Does that seem like C++ then was kind of the genesis, or where we started to see more of those complexities in the language for reverse engineering?
yeah, I mean, I think C++ is challenging in a few ways. I think one of the things is just that it's a massive language. And one of the things that's a difficult part of being a reverse engineer, or like if you really want to understand a particular application and reverse it um, to a full extent, you have to have a pretty good grasp of the language itself, the internals. Even if you're not a master developer in that particular language, you still have to understand some of course, you obviously have to understand the core language features. So that in itself is like not easy for C++ as a language as complex as C++. So that's one. And of course, just whenever any language introduces like more layers of indirection, like of course C++ does with virtual tables and supporting virtual functions, that's always going to be difficult to deal with just when you're analyzing statically, and all the other kind of object oriented uh, features. The more of these complex features you want to support, the more you have to deal with, right, that the compiler generates, which is not particularly interesting for you as a reverse engineer, but that's code that ends up there in the program that the disassembler has to analyze. It's going to be more difficult for you to weed out what is the actually important stuff that's buried in there. So yeah, I think the transition often for beginners from just plain vanilla C to C++ is really big, just because of uh, the complexities, all the complex language features that come out. And it really doesn't help, of course, like with templates, right? It bloats up the size of the binary. And then combined with the fact that I'm sure we'll get into later with Go, but like unlike something like Go, we don't have a reliable source of symbols for C++. So that really adds to the difficulty.
How do you think tooling has helped with, or maybe not helped, as I mean, we definitely will get into languages like Go and Rust as sort of the modern day languages that malware authors and red teamers are using for a variety of purposes. But I mean, how has the tooling kept up? Is it still very much it? I mean, that was, I think, the biggest challenge for me getting into just that natural progression on the learning curve, was just understanding what I was even looking at. And early disassemblers left that up to you to have to understand, and the knowledge was always a bit difficult to acquire. You'd have to find some reference in a manual somewhere, in a blog entry, and every once in a while maybe a talk from a conference to piece together. And I think that's another area maybe we can touch on a little bit here as well, is just the learning and the education and the AI, the LLM age. But how did the tools, how have the tools evolved to help with it? Are we still, is there still a lot of manual intervention that's required in order to reconstruct C++ classes to understand? Because that's ultimately the goal. You just care about what it's doing functionality wise. You just map out enough of it to understand what the purpose of the malware is.
I think I'm not a particular expert on the latest and hottest in C++ tooling, say.
Yeah.
But I guess if we just kind of talk about C++ in general, something that's been around a long time, we've reversed um, malware created in C++ for well over a decade at this point. But I would say there's no silver bullet tooling that solves some of these hard problems, as far as I can tell. Virtual tables are still annoying to deal with, although there are tooling that will help you reconstruct virtual tables and like link them more easily. So there's some quality of life improvements there, but doesn't change the fact that there are layers of indirection that you still have to kind of sort through. And then, yeah, things like templated code, that's still, in my mind at least, it's an unsolved problem. Like if you have lots of code that's generated by the standard template library, like we still don't have very reliable ways of like distinguishing between all those functions. So in some ways, yeah, those core difficulties remain. You know, obviously with the advent of like these LLM models and how great they are at code comprehension, that could significantly change potentially. Maybe we'll get very good LLM models that are really good at doing that, a lot of that deconstruction for you into something that resembles more like C++ source code reliably. But yeah, nothing that's been completely game changing, for example, for that particular language.
You mentioned obfuscations and you going back years into maybe less common. It seems like a very simplistic overview is that you know, I guess I'm not even sure. Maybe you could help fill in some of the details here. But obfuscations can come from a variety of sources. It can be a part of the source. It can be introduced by the compiler. OLLVM would be a great example of that. You can have some sort of post binary rewriting phase. If those early days there wasn't a lot, it seems like maybe the next step was packers and cryptors, and then maybe seeing more anti stuff baked into it, an anti debug or maybe some anti disassembly. What has been the shift in obfuscations? I mean, even I would say that you could see optimizations as a form of obfuscation. Where have you seen that evolution here as we're kind of working our way through the languages and some of the complexities that they introduced?
Even just say 5-6 years ago, I would say it was, we were still dealing with packers, for example, fairly frequently. Like that was always, I guess, part of the um, our landscape when I started. But I would say gradually we have more and more of these, you could call it obfuscations, optimizations, um, that are kind of manipulating the code itself, right? Rather than being a wrapper around the code. So like say packers, I think of traditionally, right? They're typically wrappers around some core program, and with enough skill, even the more complex packers, you could eventually unpack it and get to the good stuff that's inside, right? Like that's not heavily obfuscated. But gradually, with things like virtualization based packers like VM Protect, and of course, like compiler based uh, obfuscators like OLVM, I think we've just gradually seen more and more of these like tools that are doing a lot of the manipulations at the compilation stage and introducing all these things that are just you can't there's no clean way, right, for you to do that separation between what is the thing that's protecting the code and the code itself, right? So the more they kind of become right intertwined and enmeshed, like the more difficult it is for us as reverse engineers to figure out what pieces to analyze. So yeah, and that's all definitely also been a trend in tandem with like just that the language themselves and the type of runtimes that we deal with have gotten more complex. We've also seen, of course, more and more innovations on the part of malware authors and like obfuscation writers on um, these kind of tools. So yeah, it's really two pronged. They're both, none of these are really to our benefit ever. So it's always towards making these binaries more difficult to analyze.
So I think we could probably shift to more of the modern era. I say modern era. I wasn't sure before we started recording today when Go and Rust. I see those as sort of the modern languages, at least modern languages that produce native code binaries. Go and Rust have both been around since the early 2000s. It seems like they kind of early 2005 went into some internal development or beta releases before they made it public and sort of hit their 1.0 releases. So they've actually been around for quite some time. Um, is that a fair assessment of a modern language right now? Is it Go? Is it Rust? Are they the now? I mean, I know we don't have stats in front of us, but do you see that maybe from an RE perspective as more commonplace with malware authors and red teamers, and or is it just a mixed bag still of C, C++, and other other languages that you encounter?
Yeah, I mean it's all relative, right? When you're talking primarily about C++ and C, like which have been around for many decades. So like typically, yeah, I would agree. Like when reverse engineers typically talk about like dealing with modern compiled languages, it's typically the primary culprits there are Rust and Go. Um, and yeah, over the time that I've been reversing, they have really gained a lot of mind share in malware authors. Of course, in just it all kind of follows trends, right? In the general developer space. So obviously, these two languages have gotten more and more mind share from just the regular developer community. And the more these languages have evolved and gotten popular, they've spread it out more into uh, the language choices for malware authors as well. And yeah, definitely when I started learning how to reverse, these were definitely not really part of the landscape yet. Um, and over time, they've just grown and grown. I would say they're not necessarily the majority quite yet. I'd say they still each represent some not significant minority. But I think gradually we will just continue to see those languages get more adoption in malware authors toolkits here.
Yeah, and it makes sense. Certainly, as the support and the language mature and the resources to develop them, and of course, we have AI assisted development patterns now or workflows as well. That it just that they would become more commonplace. What do you see like a divide in the type of who uses these? Is there a nation states that tend to go for Rust and maybe criminal organizations that go for Go? And in researching a little bit more about the languages, it seems like Go is designed to be easy, and Rust is designed to be you have complete control, and so the learning curve is a lot steeper to work with Rust in terms of from the development side.
I guess I don't have particular insight into like attribution for whom like these things are popular, but I guess one thing that I will say is that I think the Go malware that I have seen tend typically to be um, things that uh, or at least maybe with Rust specifically. I think a lot of the Rust malware that I have seen tend to, for some reason, be ransomware. I don't know why, but that maybe among the ransomware community, that's been a particularly popular choice. And I would say like maybe for some good reasons in that like we don't have to get into it yet, but like Rust is notorious, of course, for being difficult to analyze, and maybe the more profit oriented you are, the more you have incentive to innovate on those aspects. I don't know. Whereas I think with Go, of course, there are ransomware written in Go, but I think I see more of Go being used for kind of utilities and also things that rely on some sort of networking like backdoor. Um, I'm not sure exactly for the reasons why that might be, of course, because they both have robust standard libraries that support most of anything that malware needs to do, but that's just my experience.
Okay, and maybe taking a step back, if like why would someone choose? Why would a team, a criminal org, whatever it happens to be, choose a language like Go or Rust over some of the more traditional languages that we've been discussing?
Yeah, I think some of the benefits like that we typically associate with these languages as developers maybe don't necessarily apply. I think it's a lot of it is just like comes down to uh, the reason that I think these languages have just gained more mind share is that just more developers and more malware authors, of course, have just gotten more comfortable writing these languages to begin with. Um, and I think increasingly, like everyone has wised up to the fact that like these In particular, Rust just generates malware that is more difficult to analyze and more difficult to reverse. So if I were a malware author today, for example, like I think I would definitely choose Rust, go with Rust, just because of the sheer advantages that you gain in the fact that it's like much more difficult to reverse on the side of the defenders. Right. So if you can choose a language, and of course, like code generation is a lot cheaper. Writing code is a lot cheaper these days with the help of LLM. So like if the barrier between language choice is like a lot lower, why would you not go for the languages that produce difficult binaries to reverse? That's like that's not something you necessarily rely on as a way to obfuscate or secure your binary per se, but like it's an added layer of complexity, a significant added layer of complexity. So like there's no reason for you to not to make that.
I guess what could you say then is, so like from an RE perspective, what would be some of the primary differences in reversing a Go or a Rust binary? I know that you've recently gone through a pretty deep dive in Go internals, and it's actually been published on the Flare Learning Hub. So if anybody is not aware, there is a great technical deep dive on the Flare Learning Hub. That's a GitHub repository. I'll make sure to add a link in the description of the podcast so you can check that out. But where would you see the primary differences? What really makes the two challenging, and which one would you prefer to reverse engineer then?
Yeah, so I can't unfortunately speak that much for Rust specifically because I don't consider myself quite an expert yet. But I can speak more to Go, just because yeah, I have kind of done a more of a deeper dive on just Go binaries and the compiler, and that was a lot of it was just out of the need for myself to be educated about that topic. Uh, and yeah, as it is with a lot of reverse engineering topics, there wasn't a one resource that I thought was really great at making you smarter and like more of an expert on Go reversing. So that's kind of what I started to create, and um, I would say maybe this is I don't know about a controversial take, but like my take is that I think I would much prefer reversing Go than a lot of other things in the compiled language space. And I would specifically take a Go binary, assuming these are unobfuscated. If you introduce obfuscations, maybe it's a different story, but assuming there isn't an external obfuscator in play, I would take reversing a Go binary over Rust or C++ any day. And I think yeah, so I think when you first open up a Go binary, it's quite intimidating just because, yes, a lot of things get statically linked into the binary, so it's big. It'll be several megabytes, and there will be lots of functions. It'll look very different than just something like vanilla C or C++ because the calling convention is different. Of course, the runtime is complex. There's a lot of things going on there, but in a lot of ways, the Go language itself is much more compact than, say, a C++ or a Rust. Like you could, that's part of the design philosophy of the language, right? It's intentionally designed to be compact and like easy for someone to get productive on it without tripping on a lot of really complex language features, and that really also kind of translates into uh, the binary and the compiler as well. So once you do become familiar with some of the internals and like some of the quirks of that are specific to Go, like the calling convention, it is actually surprisingly, can be a pleasant experience.
You went through the deep dive to learn the internals of Go out of as a necessary to be more effective at reversing these. I have found over the course of my career that I usually learn just enough to get by, and 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 don't always take the time or have the time to really dive deep into something. how did that process work for you? Do you can you look back now and say that that ultimately was the best way to approach it? That is to spend the time and commit the energy to really learning the Go language from the inside out, maybe. And what are maybe some of the challenges with trying to do that? You have a document that certainly encapsulates some of your learning, but it's 6 months from now, I would have probably forgotten 70% of what I learned, and I have to go and relearn it again or have a reference like you have created.
Yeah, I think I, one of the challenges is, as you say, is like when you're a professional reverse engineer for that's you're reversing malware. And maybe some of it's specific to how our team is structured and the kind of services that the Flare team provides. But yeah, oftentimes you don't have the luxury of just spending head down several months on just one specific topic, right? We're often jumping in between different types of languages, different types of malware constantly. So generally, when you're working on a sample, your focus is trying to analyze the sample, and you're not necessarily investing a ton of time into writing down all the nuances that you're picking up about that particular uh, language that you're dealing with. And so yeah, there's definitely always a need for, I think, someone to do the deep dive and do the comprehensive, like take a step back, look at the thing holistically, and then like figure out what are the things that you really need to be aware of, where if you were pressed to do so, you could really fully analyze every piece of a compiled binary. Even though that's not common, I do think it's necessary for us to have the knowledge and the quality references that we need to be able to pull those up when these things are demanded of us, which sometimes does happen. Um, I would say I really don't have a specific magic trick that I use for kind of compiling the Go reference or any of that deep dive. I did not have a particularly strong background of like compilers per se. I did have some understanding of how these things work. I think generally most reverse engineers do, but I didn't say have like a deep expertise on like an existing compiler architecture from end to end. So this was really my first time digging into that, and looking at the source code for Ghost compiler and the linker, and kind of doing that from all the way from right the lexing and parsing phase all the way to the back end. With Go, I think it's actually, if you were to choose, your first foray into like doing that kind of deep dive, I think Go is actually not a bad candidate. Of course, I can't vouch for like every other language that's out there because I don't have that expertise. But just in hindsight, it's not bad just because of, again, the fact that Go itself is not a huge sprawling language. So there's some compactness to the language itself, and the fact that like you don't have a separate backend like you do, say, with Rust and LLVM. Go's compiler and the code generation from all the way from the start to beginning is all just there in the Go compiler. Uh, so yeah, you could do that deep dive without having to go to yet another sprawling code base, right? So you don't have to deal with that jump. Um, but other than that, it was mostly just an exercise of uh, just putting the time in. Unfortunately, like with a lot of these things, it's only when you grind an infinite amount of time into the thing, and then you get some result that feels satisfying and comprehensive. At least to me, there's really no substitute. So I think a lot of the battle is just who's put the time in and who's done the writing. Um, so yeah, I think reverse engineer, like us as reverse engineers, we're always craving, I think, just deeper, more comprehensive references, just because we bounce around so much. It's just hard for us to do that build up of the topic in full. So yeah, I'd like to see more of that. Of course, more of these quality kind of references from for all the topics that we come across.
Yeah, it's difficult. I think to do that. You know, as your if your focus is on reversing something to provide capabilities or IOCs or whatever it happens to be, it's hard to also take the time to document, even if it's just for yourself, what you've encountered, what you've learned, to start building out that resource. Because usually, at least I always feel the pressure to get to the next stage and move on, unless I'm building educational content. In which case, then there's oftentimes a little bit more room to breathe there. How, how do you have a a way that you anticipate keeping up with the language as it changes and keeping references? That's always the fear, I think, on the other side of developing something, a deep technical dive or a no starch book or something, is that how long will it last before it ages out to a point of irrelevance? I mean, there will always be something, I'm sure, in the language and the core of how it works that will be relevant.
Yeah, I mean, I think there's really no way to go around the fact that it's keeping these things up to date with as the language evolves simply just takes more time. I don't quite anticipate like I think the reason why I initially wrote that was to have everything in one central location, so we're not having to pull up multiple blog posts across multiple versions of the language to have that comprehensive reference. I think dealing with changes in the language is actually something that I haven't quite addressed because when I was working on this, I explicitly you know pinned the language version and just dug into that particular version. Um, so yeah, as we get Go 1.26, 0.27 and onwards, there will be changes, I'm sure, new language features, changes in the runtime. And yeah, we'll simply have to go back and update it if I can ever find the time and energy to do that. But I think that's just simply part of the cost that like you know, um, any reverse engineer team has to kind of bake in, right? Like, there's always just maintenance cost to the tooling and the writing.
What about tools? It seems like that's oftentimes an artifact of the research. You deep dive into something to figure out how it works, and maybe some tool or some script comes out of the work to codify the thing that you learned. We have, for example, with Go Resim, which is part of the metadata recovery and the Go binaries, and maybe something you alluded to earlier, making them a little more pleasant to reverse. But that's kind of it. Is there? I, I'm not sure what I'm trying to ask here, but is there more tooling that could be done? I mean, is and we have signatures. Maybe there's definitely room for improvement there. What does the decompilation look like? I mean, is that with these languages in particular something that is satisfying? I mean, I know decompilation is still a difficult problem to solve with many languages as the source. I mean, it's all machine code, of course, that it's being recovered from. But it doesn't seem like there's a plethora of Go tools out there. Am I missing something? I don't spend a lot of time reversing Go, so I'm not sure I have a full purview of the reversing landscape of such a language.
I would say the most important tooling is already written, which is GoReSim, and that does take care of the scenario in which when you compile a Go binary, you can instruct the compiler slash linker to strip symbols, which is not actually what it sounds. I think a lot of people often get confused by what it means when a Go binary is stripped. So um, that means removing the symbol table and any of the dwarf debugging information that gets packed into the executable. But there's actually a ton of metadata, including the original symbols that are still left intact. You just have to programmatically recover those, and that's what GoReSim does. And so That is probably the most critical tooling to have in your tool belt when you're dealing with Go binaries. And when you run that, it will recover all that information, and then you can take that output and then use it to recover the symbols and the type names into your disassembler of choice. I think there is room for improvement in the Go reversing experience. I think one of the things, besides the fact that there's still some amount of metadata that we can do more effort, we can do more work to recover. I think the Go recent improvements are coming, and we're working on that. I think the other big thing is just having uh, full function signatures restored onto all the library functions. Something that is not currently happening in any tooling, as far as I can tell. And part of, if you open up a Go binary in a disassembler, a lot of the busy work is actually just fixing wrong function signatures for like common library functions. So partly maybe due to Go's calling convention and the fact that like a lot of these uh, tools are not particularly designed with Go in mind, etc. But a lot of the times the disassembler and the decompiler have challenges in getting the function signature correctly, just by looking at the binary itself, which obviously creates messy and incorrect decompilations. So that's probably the biggest jump in the Go reversing experience. But after you have those things, it's really not too bad. And I think the biggest leap in just the Go reversing experience is just going to come from having an LLM driven tool that can reliably convert from the assembly slash decompilation into Go like source code. So ideally, the ideal scenario is that you have a pretty accurate representation of the disassembly and the decompilation, along with the Go basically the Go decompilation, kind of all in tandem, so that you'll of course, there's nothing such as 100% yet, so you'll of course have to do the referencing between all those things to make sure what you're looking at in the decompilations is correct. But I really think that's where we're going in the very immediate, like very near future. And obviously, when we get there, right, that's going to be a lot faster, and a lot more pleasant experience of reverse engineering Go samples.
Yeah, I that seems like absolutely the trend in a great way. Where do you see, like at what stage then do you see the LLMs helping with that decompilation, that recovery? Is it picking up a certain, is it like the pseudocode? Is it like helping and assisting? Like if you look at something like Hexrays, they have their different and Binary Ninja, they have all their intermediate representations and their microcode and their different passes. Does it play a role in those stages as well, with shaping and structuring specific to Go syntax?
Yeah, I mean, I think actually I haven't done extensive testing. I think that's one of the things that will, uh, or maybe the reverse engineering community will have to work on, is to get kind of maybe some kind of effective way of doing benchmarking. But I would say, just based on anecdotal evidence of me trying these things, the models are already quite quite good at taking just the information that's there, assuming we are really extracting as much as we can out of all the metadata that does exist in the binary, getting that applied, taking the disassembly and the decompilation, and then feeding that into the LLM models, the latest LLM models, and then getting them to do that decompilation. They're quite good um, already at doing that. Now, of course, they're not. They still hallucinate. They're not perfect, and so that is still kind of the area where you do need some level of verification, right? So you as the human do need to have some of that understanding of Go to be able to uh, verify these things. But obviously, the models are advancing very quickly, and this just sounds like one of those tasks that these LLM models should nail. Even if it's not 100% accuracy, like if it's uh, accurate most of the time, I think we'll see ourselves relying on that kind of level of high level decompilation using LLMs. I think it'll be just indispensable for reversing a lot of these binaries in the very near future. So
With we've talked a little bit about obfuscation. Where have you seen obfuscation playing a role with languages like Go? I know there's but the only thing that comes to my mind is garble. So I think anyone who's tackled enough Go probably has come across that as an obfuscation framework.
yeah, I mean, again, just speaking specifically for Go, obviously a lot of I think generally the level of obfuscation that we see in malware somewhat follows just the availability of obfuscators for those scenarios. And for Go, like about the only popular obfuscator I can tell is what you already mentioned, which is Garble. And I think Go again, there's legitimate reasons to need obfuscators and binary protectors like Garble or any other ones. And I think for Go, it's uh, particularly necessary. Again, there's a reason I say if a reverse engineer is saying that it's somewhat of a pleasant experience to like reverse that particular language, then as a person who is doing developer, being the developer and writing these tools, right, and you have maybe code or intellectual property you want to protect, obviously there's a need for obfuscators to counter that, right? So yeah, I would say the biggest thing that you can do to really make life more difficult in a Go binary is not even doing the code obfuscation itself, is just removing symbols. And that can be done by just going through the metadata and replacing the names or scrambling them or deleting them, whatnot. Uh, yeah, as soon as that happens, then right, that's a whole different ballgame because, as I mentioned, these binaries do have very massive, they're massive statically linked binaries. So when you suddenly no longer have the symbols and you're not able to quickly distinguish between what is library code and what is user code and like which is which, and you don't have robust like signature libraries for these things, obviously that's playing a completely different game. So now it becomes much more difficult. Um, and there's other things that the tool does, but I would say that's probably the biggest piece is just the lack of symbols.
And what garble doesn't do that then? Is it mean like what does garble give you as an obfuscator?
Oh, it does that, and then it does a whole bunch of other things. So it
Okay.
tampers with metadata. It hides strings. It'll introduce like the typical kind of code obfuscations you might expect in other code-based obfuscators.
Okay.
So doing things like uh, messing with control flow and adding junk, etc., etc. So
Okay.
it's pretty full featured, I would say. Yeah, in
Okay.
terms of
Okay.
obfuscator.
How do you think that will impact then what we just talked about with LLMs and aiding recovery of code and helping with analysis?
Yeah, I mean, I'm gonna be a little careful about speaking against like one particular obfuscator, but just speaking in general about
Yeah.
maybe broadly about obfuscation and like the interaction in between that and LLMs. I do think that uh, gradually over time, like one of the key things that reverse engineers will have to deal with as a profession, I guess, or as a community is just um, making these binaries, uh, I don't know if there's a good verb term for it, but like being in a state where it's like amenable to being fed into an LLM and being solved, right? So like maybe it's like LLM input engineering or whatever. But yeah, theoretically, right? So for example, I think .NET is a good uh, example of this, where uh, .NET assemblies are very easy. There's tons of tools out there that can easily decompile .NET assembly .NET assemblies back into something that resembles source code. And so there's a huge proliferation of obfuscators there. And so, theoretically, if you didn't have obfuscated binaries, these things are LLMs are going to excel at, analyzing the code once it's decompilable back into something that resembles source code. So I think increasingly I expect just dealing with obfuscators is going to be like the bottleneck. That once you get that unlocked, it's going to mean that a lot of more of the analysis is going to be you can automate that, right? So
Hmm.
I think more and more of our time will be spent just fighting obfuscators and like getting those cleaned up to the point where we can then use automated tooling to do a lot of the more mundane analysis, right?
Yeah, I was going to ask as well about .NET because I'd feel a little remiss in this modern languages discussion. .NET certainly plays a very significant role, but you just touched on it. I don't know if there's anything more to add to it. And certainly, it continues to be popularized by malware authors and red teams for probably a lot of the same reasons as Go and Rust.
Yeah, I mean, I think I don't know if I can necessarily speak to like why a malware author would choose one ecosystem versus the other, but certainly like .NET malware is popular, and almost always they're going to be protected with obfuscators, um, and so yeah, a lot of the experience there is just a lot of the experience there is just going to be fighting the obfuscation, which can be pleasant in a way, in a strange way, like taking something that's obfuscated and then like picking it apart piece by piece and turning it into some clean looking binary is somewhat of a satisfying experience in a weird way. Like I kind of think of it as akin to like digital gardening, maybe. Like I'm not a gardener, but that's the closest experience I think we can get to like gardening as reverse engineers, is like shearing away the messy bits on a obfuscated binary. But yeah,
I spent last night shearing away the messy bits of my garden, and it is challenging, frustrating, and rewarding all wrapped up into one. So I think that's an appropriate way of looking at it. Anything that you want to cover that we haven't covered? Is there? I was curious. I hadn't really given this a lot of thought. Is there a TTD angle here that I haven't considered or is worth discussing, or just any other things that you want to maybe talk about before we wrap up?
I'm not sure about TTD. I actually haven't really had much experience working with TTD on Go, but I imagine it's maybe not that pleasant or like not that useful, because there's um I mean, typically the useful thing you're gonna get with TTD, of course, there's the fact that you can go back and forth in the debugging. But for one, I think one thing that's gonna be problematic is just it will probably blow up the trace size, just because the binaries are large and there's uh, lot of runtime code that's running. So that's, for one, makes it less useful. And then yeah, I mean, typically you're doing a lot of queries on like Windows APIs that are being invoked, but that's going to be many layers removed from the user code. Typically, like that's a lot of that's going to be buried in the runtime, as opposed to say dealing with that in a C or even a C++ binary. So I suspect it's a lot less useful for like our typically the way that we typically use it in our typical like recipes that we use. So that is my guess.
Are there any other languages that are emerging? Are we kind of stabilized on modern languages, Rust and Go? Have you come across anything else that's picking up traction? I mean, I imagine there's dozens of languages out there that aren't nearly as popular, but they could be.
I would say the ones that we've touched on are the big ones, but if I had to pick a wild card language that I see ever so occasionally, it would be Nim. Um, if I had to throw one in there just for funsies, but um, I'd say yeah, not all that common, and I don't know that all that much about Nim to be honest. So, um, but I mean, obviously, as reverse engineers, like you don't really want these things to expand because it's just like yet another thing, yet another like language stack you have to learn and deal with. But I'm sure we'll get, you know, we'll get more innovations and newer and hotter languages that we come across that we'll have to deal with. I would say the one other thing that I think where we have a blind spot, it's not necessarily a new language per se, but just a new like for you could say format, but I think uh, C or like .NET assemblies that are um, compiled into native code using native AOT ahead of time compilation. Just like .NET assemblies turned into kind of static binaries. I think that's one area where we have as a reverse engineering community. I don't really see it's uncommon. I've only seen it a handful of times. I think it's going to increase in frequency in the near future. Um, and I think it's, yeah, we just don't have much research into it. We just don't have much experience dealing with it. There's really not much you have if you're dealing with something like that, as far as I can tell. So I think that's one where we need more research, and maybe it's, yeah, hope it doesn't get more popular, but maybe that's like the wrong thing to say on a podcast.
Social media, it seems like we're kind of divided. At least the stuff that I see, I don't consume a lot of social media these days, but it's I see this sort of bifurcation of the community. It's AI is just going to be the next iteration of the decompiler. It's going to be a great aid, but it's just that we still need human in the loop. And then the other camp tends to be AI is going to take away all the reverse engineering and do all the work. Where do you fall in that?
Yeah, I mean, as a complete non-expert, I think some, I think some categories of malware, I just don't. I think we'll tend to trend more towards where certain categories of malware or like certain type of samples that are not obfuscated, we'll just not have like humans dealing with those anymore, and we'll move on to like harder and bigger problems. I mean, it's always, I think the hardest part about predicting that is, of course, this is kind of an adversarial like scenario, right? So the more capable these AI tools are going to, they become in doing code analysis and reverse engineering, I'm sure we'll get a bigger proliferation in obfuscators, and more and more sophisticated obfuscators. I think that will happen. Um, but like for instance, right, just assuming that you were able to clear away a lot of the obfuscation on say like a .NET assembly, and be able to do that with a good degree of accuracy and confidence, like I don't think as soon as that happens, right, there's no real need for like a human to do a lot of analysis there, right? Because the LLMs are so good at taking just the source code and doing the analysis and summary. With yeah. So the only barrier there is really the obfuscations that get in the way. I'm sure with I'm not quite sure what it will be with the more complex and large. compiled binaries, just because of the fact that they are large. And uh, just in the near future, I don't know if it makes that much sense to like feed in the sheer number of information and data there until LLMs and expect like very good results. But um, of course, I think in the medium to long term, that will uh, a lot of that will get solved as well. So yeah, I think I tend to lean on like we'll just be dealing with certain classes of malware. A lot of that will be automated, and we'll just move on to even more harder and even harder and even more difficult problems as we've all been gradually experiencing, right? The type of samples that we get just gradually get more complex and complex. So
Well, Jay, I think we are a little over an hour. So if there's anything else that you think we should have discussed, we certainly can add it in. If not, I think I can say thank you for your time and insight and expertise. It was really great talking to you, and we can wrap things up.
yeah, thanks. That was fun.
And that's all for this episode of Behind the Binary. Thanks so much for tuning in. If you enjoyed the show, please consider subscribing and leaving a review. It really helps us to reach new listeners. Until then, stay curious and keep exploring.